Evening, all the respected participants.
Good evening, sir. Shall we start?
Yes, ma'am, please.
Okay. Good evening, all. We are deeply honored to welcome Dr. Vikas Wasson, Director at Chhattisgarh University, Gharuan. Sir has more than 17 years of experience in the field of higher education and has been contributing in such a meaningful way to academics, institutional development, and students' growth. What we truly appreciate about Vikas sir's journey is the way he focuses on building better learning environments, ones that are research oriented, students friendly, and aligned with real academic progress. Under his guidance, Chhattisgarh University has continued to move forward with his new ideas, innovation, and a strong educational vision. We are truly grateful to have Dr. Hassan with us today. Sir, your presence adds immense value to this program, and we look forward to learning from your experience, perspective, and insights as we continue this shared journey of knowledge and development. Once again, welcome, sir, and over to you.
Good evening, ma'am. And first of all, I am extremely thankful for these enlightening words. So, as directed by the officials, so today's topic will be the role of semiconductor industries in AI, IoT, and basically what we can collectively say in the field of disruptive technologies. So, myself, Dr. Vikas Wasson, I am currently heading Computer Science Department as a Director CSC at Chandigarh University, Gharuan. It is a premier university in India and ultimately in the North Campus. Uh, I have more than 19 years of teaching experience. From 2017 onwards, I was head of the Department of Computer Science. Then ultimately, I have promoted to associate directors, and then currently I am heading Computer Science Department as a role of Director CSC in Chandigarh University. In total, I have close to 45 Scopus publications, including 5 to 6 essay publications also. I have guided more than 17 MTech students, and 5 of my students are currently pursuing PhD degree under me. So, ma'am, can I start the session?
Yes, sir.
So, the key points. The overall presentation will be divided into three halves. The first one is the overview of semiconductors. The second one will be the role of semiconductors in emerging and disruptive technologies, and the importance of semiconductors in shaping modern digital systems. Semiconductors. So we all know, we all have studied quite a lot about semiconductors. So semiconductors are basically, they are some sort of crystalline solids intermediate in electrical conductivity between a conductor and an insulator. Ultimately, we all know the conductors pass so much current and insulator, they are totally blank. So semiconductors are basically invented by some sort of intermediates between electrical conductivity that lies between a conductor and insulator. So in today's time, the semiconductors are employed in the manufacturing of various kind of electronic devices, including diodes, transistors, and integrated circuits. On the right side, there is a diagram that specifies uh, the types of semiconductors in today's time. So all the semiconductors, they are basically of two main types, that is extrinsic and intrinsic. Uh, Intrinsic is further divided into P type and N type. And we all know, due to all the factors, the intrinsic semiconductors are more popular in today's time as compared to other semiconductors. So, semiconductor chips are commonly referred to as microchips or integrated circuits and are the heart of modern electronics. In today's all the electronic components, semiconductor chips are being used and we all know about it. They are basically made from semiconductor materials such as silicon and are used to control the flow of electricity in devices. Some important applications, not limited to, of semiconductor chips are obviously in telecommunications, then industrial automations, healthcare, consumer electronics, and automations. So the telecommunications is further enlarged in 5G infrastructure and networking devices. Then industrial automation in the form of robots, PLCs, and IoT devices. Healthcare includes imaging systems, wearable devices, and diagnostic tools. Consumer electronics includes in today's time smartphones, laptops, gaming consoles, and automation include the IoT based sensors and all other things. So, types of semiconductor chips. So, the semiconductor chips are basically they are of two basic forms. They are basically in digital form or analog form. In case of digital form, they are basically in the form of memory units. That is our all the premier memories, our NAND gates, our DRAM, our volatile memories. That all are under digital. And the logical, they are basically a premier part of our CPUs at this time, our GPUs at this time, including our. And in case of analog, they are basically used to have signals including sound system, temperature, and light, and they are being primarily used to measure the real world signals and convert to data. Yes, any questions till this point? Yes, anything? Yes, yes, shall we move?
Yes, sir. Yes.
So, in today's time, the innovations, so these all are some of the research papers that has been consolidated and they have been presented in the form of this tabular representation. The semiconductor industry has witnessed groundbreaking innovations that have revolutionized technology and improved performance, efficiency, and scalability. So the advancements are in the form of miniaturization and Moore's law. That is, the transistors are becoming now smaller these days due to these semiconductors, enabling more components to fit onto a single chip. Examples: Intel's advancement and TSMC Intel's advancements in 3nm and 2nm nodes. Application basically used in smartphones, including Apple A17, high performance laptops and servers. The second advancement is in the form of advanced chip architectures. So the semiconductor helps us in new designs, including 3D ICs, chiplets, and heterogeneous integration, allow for improved performance and power efficiency. So examples includes AMD's use of chiplet architecture in Ryzen processors. So what is the application? It is basically used for HPC, that is high performance computing, and gaming PCs, including data centers and cloud computing processors. The third application in case of semiconductor industry is wide band gap semiconductors. So they basically use the materials like gallium nitride, silicon carbide for power electronics. These materials operate at higher voltages, temperatures, and frequencies. So the examples is generation based fast chargers. We all are using C type fast chargers in our hometowns or our mobile phones that are basically based upon this technology. uh, Application our electric vehicles, the EVs that are coming in market, that is basically applied on this technology, that is wide band gap semiconductors. AI based chips, the fourth advancement. The development of specialized chips optimized for AI workloads such as neural processing nodes and GPUs. Our example जो आज के time पे the in the market it is working is NVIDIA GPUs and Google's tensor processing systems are very fast processors that are basically used for based upon the philosophy of artificial intelligence based chips. So application, machine learning, deep learning, and AI software training, autonomous vehicles for real time object detection. Then moving towards the quantum computing and quantum chips. So it is based upon the concept of use of quantum bits and quantum computing principles to solve problems exponentially faster. Example in today's time is IBM Quantum Systems one and Google's Sycamore quantum processor. Its application is basically of this particular example is drug discovery and complex molecular particles. Optimization is logistic and cryptography. The next application of semiconductor industry is in the field of flexible and wearable electronics. Flexible semiconductors and thin film transistors enable bendable and stretchable electronics. Example in today's time is OLED displays and flexible sensors. And its real-time application is wearable health monitors in the form of smartwatches, fitness bands, foldable smartphones, and display. The next application of semiconductor in today's time is photonics and optical chips. Integration, the innovation is integration of light-based components on semiconductors to improve speed and efficiency. Example in today's time in real time is silicon photonics chips by Intel and Nvidia. So its application is in the form of fiber optics. The basic, we all know the communication, the speed of fiber optics in case of 5G networks. So that communication is possible on based upon this advancement. Next one is MEMS and sensors. So micro electromechanical systems, that is MEMS, combine mechanical and electrical systems for sensing and actuating. Example is MEMS accelerometers in smartphones. Its application is automatic applications including airbags, stability control, IoT devices like smart thermostats and wearables. Moving on, the next advancement in case of semiconductor industry is energy efficient chips. So it focuses on reducing power consumption using technologies like FinFETs and gate all around transistors. Example in today's time is Samsung's GAA transistors for power efficiency. Its real-time application in today's time is mobile processors in smartphones for extended battery life, low power IoT devices or smart cities. The next advancement in the case of semiconductor industry is edge computing and IoT innovations. So it basically the innovations is in the form of chips optimized for edge computing, allowing devices to process data locally instead of relying on the cloud. Real-time example, the industry that is basically using this VPU for edge-based AI applications. And the real-time application is in the form of smart homes, autonomous robots, and serverless cameras, including industrial IoT, that is predictive maintenance and real-time monitoring. I am stopping here only, coming back to all these slides one by one again. So the current pichle in the last few years, last 5 to 10 years, what are the different areas in which the semiconductor industries grow, so that you all can be familiar about that. I have tried along with my research supervisor, research students, to cultivate all these things on a single thing. So all these things in the last 5 to 7 years, 5 to 10, 20 years, these had been very, very popular in the market. And this is only possible because of the growing field of semiconductor industry in different fields. So one by one, you people can also so see it. Yes, any questions till this point? Yes, yes, anything? I am again reading one by one only the advancements. That is the application areas of semiconductors, including the semiconductors, including the high performance computing and gaming PCs, including our electrical vehicles, EVs, for smart power management. Then we have AI based chips that is basically used for neural processing units and GPUs. Then we have quantum computing and quantum chips. Then we have flexible and wearable electronics. Then we have photonics and optical chips. Then we have automatic applications including airbags, stability control, IoT devices, including smart thermostats and wearables. Then we have energy efficient chips that includes the battery life of smartphones. And that last one is the edge computing and IoT innovations, including the smart homes, autonomous robots, and surveillance cameras. Almost covering all the things. I'm stopping the sharing screen here only. Coming back here. Yes, anything, anyone who wants to discuss it so that we can move forward. I request everyone, anyone who wants to elaborate the things that we have discussed in the last few slides. any more enlightening points that I have not covered? Obviously, we will cover the more things in the further slides also. I request my fellow colleagues, anything that you want to add in this.
So participants, please respond.
Is anything? Otherwise, I will move to the. So, moving on to the next slides. Yes, visible.
Yes, sir. Yes, sir.
So, moving on, the current top 10 semiconductor trends and their innovations. The trends are includes basically the industries where the semiconductors have boomed in the last few years. That is, the semiconductors are a prominent field in today's time, and basically the innovations. Is my slide visible?
Yes, sir, visible.
Yes,
And
visible, sir, but I think the slide is not moving.
give me 1 second. Give me 1 second. Is it visible now?
Yes, sir.
Yes, sir.
Top 10 semiconductor trends and innovation. Sorry. Hanji. In today's time, the semiconductor industry has evolved in almost all the fields. The premier application areas in the semiconductor area will be it is in the basically used in IoT, that is the field of Internet of Things. It is basically used in 5G technologies. It is basically used in artificial intelligence based chips. It is basically used in in-house chip designs for the home smart applications. It is used for advanced materials. It is used in fabrication technologies. It is basically used for novel architectures. It is basically used in automatic chips. It is also used in advanced packaging, and it is also used for sustainable manufacturing. Some of the startups that has been also elaborated with, sorry, the picture is not very much clear due to the space constraints of the page. So, but it is being used almost in all type of industries. Yes, we are nowadays we are very heavily talking about the concept of industry 4.0. So moving upon this era, industry 1.0. In at the time of industry 1.0, the steam power drives the shift from manual to mechanical production in the late 18th century, increasing efficiency and laying the foundation for industrialization. Then, after 100 years, we have shifted towards Industry 2.0, and our focus is shifting towards in Industry 2.0, the electricity and assembly lines revolutionized manufacturing in the earlier 20th century, enabling mass production, standardization, and improved productivity. Then we have shifted to Industry 3.0 in the year 1970s. So ultimately, we are moved towards the late 20th century witnesses the rise of computers and automation, transforming manufacturing with programmable logic controllers, robotics, and advanced technologies. So currently, we are slowly from the last 10 to 15 years, we have moved towards the Industry 4.0, where the current era employs smart technologies including IoT, AI, data analytics, integrating digital and physical systems for enhanced efficiency, customization, and decentralized decision making. Some facts: 67% of capability most equal to metaverse development. 37% of the respondents believe sustainability will likely play the largest role in the semiconductor value chain within the next 5 years. Then there is mobility. 93% of the executives thinks motor vehicle manufacturing companies should partner with technology companies on the next generation mobility. And the digital health, 28% of the respondents believe wearables will benefit the most from continued semiconductor innovation. So what we want to say is, even though the semiconductor industry is evolving, but the future scope is very high in every field, including the metaverse, sustainability development, mobility, digital health. Semiconductor industry will play a major role in the coming years. So, but every positive side is having a flip side also. So these are some of the greatest challenges for the semiconductor supply chain. That is, the first one is 35% there will be the chances of inflation, economic concerns. Obviously, with this all these things, we are coming toward technology. Ultimately, it results in economy, inflation, महंगाई, that all things also. 20% is still, the businesses are still lingering towards the COVID-19 implications. 18% talent is in pipeline. 14% there is a greatest challenges is lack of investment. Still, investors are having a fear for investing the sum, and there is 12% of the cases there is geopolitics. So factors with the greatest impact on semiconductor innovation in near future. 48% chances is that ecosystem considerations like chip and geopolitics that ultimately affect the business of semiconductor industry. 42% chances is because of cyber security. And ultimately, everything needs to be changed with a particular time. Ultimately, the 39% greatest impact on semiconductor innovations will be based upon changing competitive landscape. That is, we want ourselves to shift to a new technology that ultimately reflects to a semiconductor innovation also. So, sustainability of semiconductor technology. So there will be a very high chances that semiconductor technology will have a sustainability effect, and that is because of the following factors. The first one is AI is very high computing power intensive. For example, a chat GPT search consumes 13 times as much energy as Google search. So we want some sort of battery backup procedures with the help of semiconductors. Then companies should design for sustainability. That is, there is a strict need for dedicated engineering teams to support sustainability goals, including equipments, SAPFAB, process recipes, and operations. Companies such as Intel and Applied Materials have engineering dedicated to sustainability as part of the engineering ports. Every semiconductor company has thousands of suppliers that include Intel, for install, has 16K suppliers. However, most suppliers have yet to set their sustainability goals. Therefore, it is an urgent need to establish matrices and develop a measurable roadmap to achieve net zero. Further, the digital technologies can help reduce the carbon footprint and make fabs more sustainable. This can be achieved by optimizing efficiency through advanced analytics, improving digital lifecycle, collaboration with fabs. Companies have made more progress on their US sites than in the other regions. For example, Intel and STM Micro are net positive water in the US but are not in other regions. Digital twin offers fast scalability. So, device that scale twins include detailed visualization of a device to reduce cycles of silicon learning, reducing waste and resources. Then includes process scale twin that uses simulation to streamline process development. Sorry. Then there is equipment that are improving fast time right from design through installation by finding issues before physical building. So now come to the main thing, that is the innovation of semiconductor design and manufacturing using various disruptive innovations. So there will be various fields in which these disruptive innovations can be moved forward. Yes, I want before moving forward anything that any collaborative thing that you want to share with us.
So your voice is not audible.
Sir, your voice is not audible.
Because sir, can you hear me? Hello.
Sir, you are muted, sir.
Sir, so your mic is not in unmute.
Yes, is my mic audible?
Yes, sir.
Okay, okay. Ji. Yes, anything before moving? Sorry, there was a. Yes, can we move?
Yes, sir.
Sir, I think Ravi Kumar sir raised the hand.
Yes, yes, please, sir. I am waiting
Ravi Kumar
so
sir.
that it should not be a one-way communication.
Sir, can you elaborate a little bit on digital twinning of the processor or SoC?
Give me 1 second, sir. Moving. Screen visible? Yes. Yes, is the screen visible?
Yes, sir.
Now, ultimately, as we are evolving towards the various fields, we people have to scale how the scalability issue will be resolved in this using semiconductor industry. So there are number of techniques, because ultimately I have gone through this from various research and review papers. Ultimately, the scalability issue is more improved by using device scale twinning. So there will be three techniques that are basically used. One is the device scale twinning, the second one is process scale twinning, and third one is equipment scale twinning. In case of device scale twinning, we are having a detailed visualization of a device to reduce cycles of silicon learning, thus reducing waste and twisting. Instead of going towards again reprocess, the processor is used again and again. What is going, a thing is used one time, and ultimately the visualization is created, the samples are created on the base of visualization, so that at the time of production there will be less waste and of resources and other materials. Then the second case is the technology that is currently being used is on the basis of process scale twinning. That is, they are basically using simulators to streamline process development, and this particular process will ultimately reduce the chemicals and electrical usage. Then the third case of digital twinning is to increase the scalability is it is on the based upon equipment scale. That is what they are doing is they are improving the first time right from the design through installation by finding issues before physical build or building equipment expertise faster. So what they are doing is they are basically improving the performance of a silicon based components by using some sort of techniques that are basically help in longer term and faster operations. It can be on the basis of device scale, it can be on the basis of at the time of processing, and it can be even at the base of equipment build up. That is the thing is being done at the time of building the equipment itself. Yes sir, Ravi ji.
Fine, sir. Thank you.
So moving ahead. Yes. So the innovations that ultimately will grow the semiconductor design in industry more popular in the coming days. The first one is the chiplet architecture. That is, we people with the help of semiconductor industry, we will modular approaches to chip design and ultimately it will improve scalability and performance. The second main thing that can be innovated is in the form of 3D integration. That is, we people will have, the industry will have vertical stacking of chips, increases density and efficiency. That is, more and more number of components will be installed at a small space. Then we have a photonic chips. That is the use of light for data transmission in semiconductors for high speed operations. Then we have advanced lithography. That is extreme ultraviolet lithography enables -7 nm process nodes. And then the latest innovations can move to ultimately the flexible and organic semiconductors that are ideal for variable and flexible displays. Some of the future trends. The first one is neuromorphic computing. That is the chips mimicking the human brain for advanced AI. That can be a future trend. Then there is AI driven chip design that includes automatic design processes, reducing development time. Then there are graphene and beyond based materials that ultimately paves the way for post silicon era technologies. And there also may be decentralized fabrication models, including potential shift to localized manufacturing hubs using additive manufacturing. Yes, the semiconductors in the drone industry, they are very popular and they are basically coming up. So the semiconductor based drone systems, they are basically crucial for future of autonomous flights, providing the technology needed for precise navigation, real time data processing and enhanced performance. These advancements are set to revolutionize various industries. So see the report, the drone chip market. The drone chip markets are size is expected to be worth around USD 9.3 billion by 2033, growing at a per year rate of 7.4%. So these are the examples where the semiconductors are being employed in the drone industry. So see the case in remote control, in case of iPad, in case of motor, in case of propeller, the semiconductor is being used for GPS antenna base. It is used for flight controller. It is used for smart battery systems. It is also used for landing gears. Almost all the components of a drone technology. So semiconductor is also evolving very much with the help of AI based techniques. Basically, the semiconductor physics has enabled us to understand the AI paradigm in a wide range of matter, including the energy and space-time skills through data, knowledge, priors and laws. Many digital consumer products in everyday life, such as mobile phones, smartphones, digital cameras, televisions, washing machines, refrigerators, and LED bulbs, also they are using the concept of semiconductors. Some of the popular is AI Accelerator, a specialized semiconductor component designed to accelerate AI workloads by performing high-speed computations and optimizing the cost and performance of AI algorithms in data centers. Yes, an important survey. The important survey is the Global Semiconductor Foundry Market Share 2025. So, and the second survey shows us usage of semiconductor across engineering fields. So see the case in almost all the industries. In almost all the industries, the role of semiconductor is growing day by day, including electronics and communications, 20%, then chemicals and materials based industry close to 5%, automation 7%, in the field of renewable energy and civil smart infrastructure, in the face of aerospace and defense, in the field of biomedical sciences, in the field of mechanical sciences, in the field of computers and IT, in the fields of electrical power, almost in all the sectors, the semiconductor industry is growing day by day. The dependency of semiconductor and AI towards each other. Yes, the essential, demand, dependent, and manufacturing. So the semiconductors are essential for AI in providing the required processing power, because ultimately all the semiconductor devices, including IoT devices, they are battery based mostly, and with the help of semiconductors they are very prominent to have batteries that will have a longer life and demand. The second one is the demand. Semiconductors for AI will grow exponentially in the coming years because we are having lot of new inventions in the coming years. Accordingly, the semiconductor industry will grow in the coming years also. The third one is the dependency. The future of AI is highly dependent upon the semiconductor industry's roadmap, because ultimately AI is basically a set of algorithms in which advanced machines, including the robots, drones, that will be built. But we all have to understand all these things are being ultimately monitored with some sort of remote controls, some sort of precision hardware, and here the hardware, the smart hardware, what I can say, the smart hardware, that the evaluation of AI is basically dependent upon the smart hardware also. And here the smart semiconductors are coming into picture, because they are basically the one that are basically helps us to monitor the things and make the new hardware advanced possible. And the last one is the manufacturing. That is, the semiconductor equipments and materials are also essential factors in the production of AI based chips. I am stopping here only, requesting my colleagues to have some sort of, yes, yes, requesting my colleagues, yes, yes, anything.
Sir, good evening, sir. Ravi Kumar again here.
हाँ जी, good evening, sir.
Sir, we started with our students on risk-based simple SOC designs, sir.
Okay.
Like, can you elaborate on what is the potentiality of startups and like how we could plan further?
The thing is, sir, in the last few years, ठीक है, ultimately the gear is shifted towards, earlier we people were more inclined, the Indian market, they are basically more inclined towards VLSI based industry, the small various hubs. But in today's time, the role of semiconductor is more advanced in the last 5 to 7 years, and that is possible only because of this AI and IoT based industry. So your market is towards, sir, risk, Raviji.
Initially, we planned for IoT gateway, sir, risk-based
Okay.
SOC design for IoT gateway. And
Okay.
we are planning further to work on just now you mentioned drone controls also we started.
Yes, yes, yes.
And how to plan in an academic setup, like how to plan ahead and
The
get a
thing
little
is,
bit of
I think
funding.
so. I think so. What we have planned right from our semester number one, we have given our semester number one. We have a dedicated course of uh, introduction to IoT lab. So what we have done is here is in the form of IoT, we are giving some small practicals to the students in the form of weather forecasting, smart agriculture. Then there is robot path planning. Small, very very small practicals that are easily available. So ultimately, what we are doing is in the academia, when the students are growing up in the second year, we basically comes up with the interfacing of our IoT based kit with Arduino systems, our ESP32 board, so that students will have more advanced versions of the products, including the products for path planning, the products for weather forecasting, and in especially to circuit branches. What I can elaborate to EC, electrical, mechanical, civil, they are basically because computer science people are more inclined towards software development. They are more inclined toward data structure, C, Java, Python. They are basically machine learning applications. But the core branches, including electronics, they are more inclined towards the antenna design. They are basically having, they are giving a lot of options. We have a specified set of electives bucket that are being provided to students, and that buckets are not limited to one. They are basically inclined towards VLSA design, then there is embedded systems, then they are antenna design, then they are IoT based disruptive technologies, and so on. So we are having a very very progressive thing in the case of structure. Also we are having a academic syllabi also that can be increased day by day, because ultimately we all have to understand the industry can be boomed only then when we people, when we academicians are sending some sort of trained students. Last also some of our students have went to ultimately the central facilities of NITTTR to have their antennas checked, because ultimately we all have to merge from one form to another. We have to have some sort of collaborative research to have such top our students can be then only market ready. Yes, Raviji, I also request you to have some sort of elaborate about your product also, what you are currently developing,
Yes, sir.
what thing you are processing, how it can be more elaborated.
Sir, as I mentioned, we started working on like SOC for IoT gateway, sir.
Okay,
And
so how you have
basically this
integrated
was
that
done
thing
by
with,
third year people. Basically this was done by
how you
third year
have
people.
ultimately the student has reached to this point that they are started to integrate the gateways. So my request is, how can you elaborate how you have integrated all these things to third year, because we cannot directly jump to that thing, na? So there must be a pathway for the students so that they can move from one path to another path. So how you have prepared the that your students currently have reached to this point? There must be some pathway that some of the things will be a prerequisite at first year, then some of the things are at the prerequisite of second year, then they have come to this point that they are being basically doing this thing. So can you elaborate on
Sir.
that point?
Sir, basically those are all electronics and communication students at the second year level. They had courses on digital design, and
Yes,
subsequently we are having in the professional elective.
microprocessors, digital logic,
Yeah,
they have
next
digital
one.
electronics.
Then at the second year level, they're having an professional like open elective in the open stream. They are opting for IoT, and subsequently, like basically there is two things. Like we
So
have
what is the
given.
procedure of giving that? Because all the students are not want to go to a single career choice. So how a
Here it is
particular,
not given to sir. The project is not given to all the students. So one project we are working on this. Like what I was
oh,
asking is, we are working on a project on IoT gateway SOC design, and
okay,
what I have asked you for is like how I could that could be translated to further into an incubation to startup kind of thing. That picture I was asking.
okay. So I have you got a TBI in your institute?
Like as of now, we are getting support from VLSA Society of India. This was
Okay,
shortlisted for One Tops program. That's how we
okay,
started, and we have TBA support also, and we have to
okay.
that we have to do for it, but
Because
not for this particular
ultimately,
project.
what basically is the thing is what we have in our institute, we are having a dedicated TBI. So what they are doing is, firstly they have shared a presentation template to all our students who those are explorer. Then they are taking the proposals from the students, and they are connecting various government agencies, including the center based IITs, NITs, and they basically, and industry also, for the funding support as well as the technology support also. So we can also plan such type of things if we want to have such type of, using the industry links, including your TBI based links, we people can move on to that particular what we can say commercialization of the product.
Okay, sir. Okay.
Yes, is the screen visible?
Yes, sir.
Yes,
Yes.
sir.
Yes, sir.
Yes, the semiconductor also plays a major role in our everyday life. That includes communication and technology, information technology based systems, the transportation and automotive industry, the healthcare and medical devices, energy generation and management, entertainment and consumer electronics, and it is also being used in aerospace and defense systems. It is also being used in home appliances and smartphones. So, the impact of AI in advanced semiconductor design. So it ultimately is having big role in semiconductor design, that includes addressing hyperconnectivity. It also is having a role of computer systems in analyzing data and executing complex computations. Then the big data and EDA transformations, they are basically having how this AI based influences electrical design and automations. Then it also helps us in designing the components of EDS. Then they are also helping providing AI integrations. Then they are also providing help in automated design insights. They are also helping boosting the productivity of the machines by leveraging historical data for peak engineering products. And they are also providing the support for consistent quality products. That includes the outcome of increased engineering team productivity. So some of the IoT based applications that uses semiconductor technology. So it is not limited to these only. So that include the smart vehicles, including sensors to detect pedestrians, road signs, and other cars. That includes the microcontrollers, processors, memory chips, and wireless communication models. That also semiconductor manufacturers are constantly innovating to meet the evolving demands of IoT, including developing advanced fabrication processes, integrating artificial intelligence and machine learning capabilities, then addressing challenges related to security, interoperability, power efficiency, and scalability. So, importance of semiconductor in IoT. So, the rise of IoT semiconductors, that includes IoT based microcontrollers, IoT based connectivity chipsets, IoT security chipsets and modules, and please see how the market is evolving. Currently, from 18% IoT NC penetration to increase 29%. Then we have IoT AI chipsets that is growing 22% every year. So this is the global market growth of IoT AI chipsets. That is from 2009 to 2005, 25. That is the last 6 years. The market has grown close to 6% in the field of IoT based AI chipsets. So the future of semiconductor education is, these are the some of the emerging technologies. That is AI specific chips, that includes the specified processors like GPUs, TPUs, and NPUs to accelerate AI tasks. Its application is basically data centers, self driving cars, smart devices, and the examples where it is being used is NVIDIA GPUs and Google TPUs. Then the emerging technologies can be supported in the form of quantum computing chips, that includes use of quantum mechanics to process complex computations far beyond classical computing capabilities. The application areas include cryptography, simulation, optimized problems. Example is IBM Quantum, Google, Sycamore. Then there is silicon photonics, that basically is a technique by which using light based circuits for faster data transfer in computing and communication. The application areas are data centers and telecommunications, and the real time example is Intel silicon photonics for optical interconnects. Then there is wide band gate semiconductors, that includes materials like gallium, silicon, and the example is electrical vehicles and Tesla. The gain chips in Tesla is the real time examples, the industry where it is being used. Then there is edge AI chips. The description is they are basically used for creating low power AI chips for real time processing at the edge, reducing latency and dependency on the cloud. The application areas are IoT devices, autonomous systems. Then there are flexible electronics, where the emerging technologies and semiconductor plays a pivotal role is thin film and flexible semiconductors for wearable devices and bendable screens. Real time example is healthcare wearables, rollable displays. Example is Samsung flexible OLEDs. Then there is neuromorphing computing, that includes brain chipset designs that mimic neural networks for low power and high efficiency computing. Example, our robotics and our AI systems. Then is micro electromechanical systems, MEMS, that ultimately the description is miniature chips combining mechanical and electrical components. The application areas is including sensors in automotives, wearables and smartphones. Then the emerging technologies is 3D IC and advanced chip packaging. So the description is integration of multiple chips into vertical stacks for improved performance and reduced latency. The application areas are smartphones, gaming consoles, data centers. And the real-time example is AMD 3D V cache technology. And the next is the low power and next gen nodes, that includes transistor advancements like gate all around and FinFET at 3 nm and below. Application is energy efficient devices and advanced processors. So real time example is the Samsung 3 nm nodes. So AI in disruptive technologies transform industries and offer replacing existing solutions and creating new markets. So the disruptive technology is AI in semiconductor design. That is, the description is use of AI tools to design, optimize and test semiconductor chips faster and cheaper. Application is reduce time to market for new chips. The next disruptive technology is quantum disruption. That includes quantum processors threatening traditional classical semiconductor dominance for specific computations. Application is breaking encryption, solving complex problems. Then the disruptive technology is flexible and printable electronics, that ultimately result in low cost and printable semiconductors for flexible displays and sensors. The application area is rollable TVs, healthcare devices. Then there is photonics based disruptive electronics, that includes optical interconnects, replace electrical circuits for faster and energy efficient communication. The application area is high speed data transfer in telecom and computing. The next disruptive technology is blockchain and cryptographic chips to enhance secure transactions and blockchain processing. The application area is cryptocurrency, mining, secure communications and basic use for SKIs for blockchain processing. It will be in the form of robotics and IoT in fab labs. Then there is the disruptive technologies, electric vehicles and ADAS. It basically is used in semiconductor powering electric, including autonomous driving and ADAS features. Then there is healthcare disruption that ultimately results in advanced chips for wearables, diagnostics, and healthcare devices. Then there is sustainable and green semiconductors. Then there will be AR, VR, and immersive technologies. So ultimately, what we can see that combining the fields of disruptive technologies and semiconductors, we people, lot of evaluation will be possible in the coming days in the field of semiconductors by making all these markets wide open. So some of the case studies that we are having in the previous few years. Yes, the first one is our NVIDIA's role in healthcare. Our daily life example that is basically moving on in a very see the case. NVIDIA in today's time, they are creating GPUs, that is the graphics processing units, and they are initially targeting graphics incentive applications. But in today's time, in today's way, NVIDIA's healthcare is basically moving towards very high, and ultimately it basically moves towards AI workloads. They are basically moving towards technology shift, market impact, ecosystem change by evolving all these things, and they are now creating a lot of applications in the case of AI hardware by increasing day by day. Then the second case study in this field is quantum computing and semiconductor. The real-time example is IBM's quantum processors. So what they have done is they have ultimately the quantum computing demands which rely on non-traditional materials and manufacturing processes distinct from classical semiconductor processes. So what the impact is basically is they have redefined semiconductor manufacturing and materials. And what is the impact? The material science innovation, that is the need for superconducting materials, manufacturing challenges, and long-term shift, that is while still in its inefficiency, quantum computing challenges traditional semiconductor dominance and paves the way for hybrid systems integrating classical and quantum processes. The case study number 3 is the neuromorphic computing. That is, the example is spiking neural network chips, SSN chips, very popular for neural network. So what they have done is traditional von Neumann architectures suffer from memory bottlenecks and high energy consumptions when executing AI workloads. So neuromorphic chips emulate biological neural systems. So what is the impact? There are 3 things, that is ultra low power. Now the power are very reduced by using these chips. Then they are also engaged towards real-time learning, and they are also moving towards new AI paradigm. The fourth case study is in the form of 5G technology and semiconductors. The real-time example is Qualcomm and 5G modems. We all are using 5G, and Qualcomm is a very famous product in these days, and they are basically used for 5G modems. What they have done is the global rollout of 5G networks required a new generation of modems and RF front-end technology. Qualcomm played a pivotal role in developing 5G enabled semiconductors. So with this, integrating this 5G technology and semiconductors, we are able to have modems that are created for 5G networks. The impact is technological advancements, that is the Qualcomm's Snapdragon platforms with integrated 5G modems push the limits of semiconductor design, requiring smaller nodes for energy efficiency and speed. Then there are supply chain shifts. The demand for 5G chips ultimately invests in advanced fabs, particularly by Samsung. Then there is competitive landscape. Companies like MediaTek and Hyundai followed suit, and they are intensifying competition in mobile chipsets. Then the case study number 6 is Internet of Things and Semiconductors. The example is ARM Holdings and IoT processors. The context is IoT devices from smart thermostats to industrial sensors. They require semiconductors optimized for low power and high efficiency. The ARM's microarchitecture became the backbone for such devices. The first impact is design paradigms. That is, the ARMs are low power chip designs facilitating IoT based rapid adoption, especially in edge computing scenarios. Then there is ecosystem growth, that is the proliferation of IoT created a demand for new semiconductor designs, including system on chips with integrated sensors and connectivity modules. Then there is market expansion. The IoT wave significantly broadened the semiconductor industries addressing market, pushing it valuable beyond traditional computing and mobile centers. Then there is advanced packaging and chiplet and semiconductors. The example is AMD's chiplet architecture. So traditional monolithical chip, the context was traditional monolithical chips. When they designed, they are facing challenges like yield issues, escalating cost at smaller nodes, AMD pointed out. So the impact is cost efficiency by using smaller modular chiplets interconnected via advanced packages. AMD reduced production cost while maintaining performance. Then there is performance gains, that is the chiplet based designs allowed for scaling performance without requiring a single massive die. Then there is industry adaptation in which the Intel and other major players are now adopting chiplet architectures, indicating a shift towards modularity in semiconductor design. Then there is autonomous, the case study number 7, the autonomous vehicles and semiconductors, that is the Tesla's FSD full self-driving chips. So the context is autonomous vehicles require specialized semiconductors for processing sensor data, AI computations, and real-time decision making. Tesla develops its own FSD chips to optimize for these techs. Impact: in-house development, new benchmarks, and ecosystem ripple. Case study 8, silicon photonics. That is, the example is the optical interconnect chips in AI data centers. Context: electrical interconnects face fundamental bandwidth, latency, and power limitations in modern data centers and AI accelerators. Silicon photons integrates optical components with semiconductor manufacturing. Impact is the bandwidth scaling and the energy reduction. So summary of all these case studies: the technology, that is autonomous vehicles. Example: Tesla FSD chips. Key impact: automotive AI's acceleration. The technology, that is Edge AI. Example: tiny ML SoCs. Key impact: on device intelligence. Technology: quantum computing. Example: cryptogenic ICs. And the key impact is scalable quantum systems. The technology is silicon photonics. Examples: optical interconnects. And the key impacts include AI data center cycling. Then the technology is 5G and 6G. So we are having new transceivers, and the impact will be next generation connectivity at a very faster rate. Then there is new form AI. So the example is SSN chips, and the key impact is energy efficient cognition. And the technology is green energy. Example is SiC power devices, and the key impacts are sustainable electrification. So these are all the references that has been used. The publications from where the data has been extracted. Thank you. Yes, any queries, any questions? Yes, any queries, any questions, or any further discussions required on the agenda?
If you have any questions, please feel free to ask.
Because what we all know, what is the basics of semiconductors. What I, along with my scholar team, what we have tried to do in this presentation is the work, the case studies of real-time problems that has been evolved with the help of semiconductor and AI in IoT in the last few years. That is the primary motive. Yes, any further discussions required? Yes.
Sir, I think no more questions.
Okay, ma'am.
Okay. Okay, sir. Thank you so much, Vikas sir, for
Thank you.
sharing these insights on today's session. It was truly help to us to understand how artificial intelligence is transforming semiconductor designs, development,
Because
and
what the main emphasis of my session was ultimately the real time case studies in which ultimately the market is evolving in semiconductor, and with this oil, the case studies of all these things, the Tesla and all these things that has been currently evolving, that are only possible because the semiconductor industries and the disruptive technologies, they have joined hands, and ultimately they are progressing towards the mankind for all these improvements that are very much required.
yes, sir. We really appreciate the clarity and the depth that which you explained the concept, and we are very grateful for the time and the effort you devoted to today's session. Thank you
Yes,
so much,
thank you
sir.
so much, ma'am. And I'm extremely thankful to all the dear participants for their patience listening, for motivating me, because ultimately the field is a very, very evolving, and it is having a lot of scope in the coming 10 to 15, 20 years, because mankind is moving towards complete automation, and the automation is not possible till we are joining heads with our IoT based sensors, and but that sensors require the evolving of semiconductor industry at a very, very high pace. Thank you everyone. I am extremely thankful to all of you.
Thank you, sir.
Thank you, ma'am. Thank you.
Simi, I think we can start the next session.
Yes, sir. Yes.
Yeah.
So without any delay, let's start our next session. So our next session is handling by our respected resource person, Mr. Ayyappadas PS. Sir, can you hear me?
Yeah, I'm able to hear you. Okay.
Okay, it's my pleasure to welcome Mr. Ayyappadas PS, specialist in embedded software engineering at Bosch Global Software Technology, who join us today. With over 12 years of industry experience in embedded system and automotive software development, Sir has contributed to multiple embedded software projects within Bosch, involving development, integration, testing, and optimization of automotive and real-time systems. With his strong technical background and hands-on exposure to industry standards, SAR brings valuable insights into the application of embedded systems in next-generation automotive technologies, safety-critical systems, and intelligent control solution. We are indeed honored to have Sir with us for this faculty development program, and look forward to learning from his rich industry's perspective and expertise. Sir, we warmly welcome you to the sessions, and with that, we invite you to lead us through the session, sir.
Yeah, thanks for the introduction. Actually, so good evening, everyone. Okay, so it's a pleasant time to talk to you on this uh, uh, technologies, and I have been to the embedded industry like it's my 10 plus years. I started with Geo as a application, then moved to the driver side with mobile, then I moved to Intel for my Bluetooth drivers, then I came back to Bosch with the ADAS systems, autonomous driving. Then I moved back to my old domain where I started only with the infotainment domain. And my area of industry is the next device drivers, and but I will give a glance through the to the hardware part or the VLSI VHDL topic today on the chip point of view. Uh, oh, excuse, can I? Yeah. So today I can. So any doubt you can stop me at any time on that slide which I'm presenting. So basically, I'm from the embedded domain. My master's was in embedded domain, so I have few.
Excuse me, sir.
Yeah.
Sir, you are sharing your slide?
No, no. Get to start. Get to start. I
Yeah.
just.
Yeah, okay. It's not visible. That's why I asked.
Oh
Sorry,
yeah.
sir.
Yeah, sorry. I'll start now. So I am from my master's in embedded systems, but I just have some passions on the VHDL. My final year tech project was on the VLSI side. So I'll
Sir,
just
you're not audible. Little
Yes,
louder.
sir.
yeah, okay, fine. And now it is fine now, or I have to still increase my voice. Is
Sir, okay.
it's fine or
It's fine, sir. It's fine.
Now it is okay, sir. Now it is okay.
yeah. So my master's was in embedded systems. So I have passion onto this VLSA. So I will share my thoughts on the VLSA. Anytime, if you have any doubt on my slide presenting, please stop me. I will explain. Okay. So we'll start now. I'll just try to present the screen. You're able to see my screen or?
No, sir, it's not. Yes. Now it's visible.
Okay. Yeah. So basically today's topic is field programmable gate array based hardware accelerators for the high performance computing. Okay. So we will split the topic. FPGA, you guys will be knowing better than me. And the hardware accelerators may be a new term which you may not hear. And high performance computing, again, some terms which the industry uses. Okay. So basically, I'll explain this term is so hardware accelerator is designed to do a specific function much faster and efficient. That is the purpose of a hardware accelerator as an accelerator to do if the accelerator pedal in a car or in a bike, you can see that what it does. It makes it fast moving, right? So hardware accelerators are designed to do this kind of operations faster. Suppose, for example, if you have an HDMI cable, you have seen it. So it will perform only the HDMI function, right? So those kind of applications we can say as a hardware accelerator. And how an FPGA will be able to do those kind of hardware accelerator for a high performance computing. So where energy, performance, all matters. So that is a topic for the day, and a warm welcome to this topic. We'll discuss all with this topic. Your thoughts, my thoughts. Any point of time in the slide, you can stop me. We'll have a discussion. Okay. So that is the agenda for the day. Hope we'll proceed further. And what we clear today is like the introduction to the high performance computing challenges. What are FPGAs? Is just the very basic of electronics. Then why the FPGAs are basically used for the high performance computing accelerations, architecture based accelerator, the FPGA based for an architecture of that point of view. Then the key domains where we use in the industry and case studies in the research, what is happening on the research side. I think the audience are from the faculty, students, so it may help you. And development tools. What are the tools currently, the applications which we have of my knowledge, and I also discussed with my friend in Intel on this after these discussions, after the PPT presentation. So his thoughts is also there in the PPT. So he told the tools which they are using, and the challenges and the limitations which we have in the FPGA, and the future trends. What on the research side, if you are very much passionate for as a research scholar to the FPGA, what all things you can do. That also I can guide you of my limitations and knowledge. Okay. Basically, I told I'm from the Linux DOS driver side, so I'm purely an OS guy, OS writer, but I will try to help you guys on this topic of my where the Linux drivers is trying to call the FPGA. So that's what I was able to take the topic for you. So when we write a driver, there will be a number of hardwares where we have to write a driver. So one such will be an FPGA also will be there. So we say like a C function, main function, we have a probe function for the driver. So at that time, we'll be calling the PMIC or the power supplies for the FPGAs, and we'll start coding. So at that time, I have seen some FPGAs and how we are going to work with that. So that's the interest. That's the way I reached to the topic of FPGA and how we'll proceed further. That. Okay. And anytime you can stop me in the discussion. So as I told, a hardware accelerator will perform a particular task in involving the to finish a particular task, as I told, like a HDMI camera sensor. So it will try to make it fast the things. So there are like traditionally, if you go to any computing or any CPU or GPU kind, any computing, we have the three walls, which we say power wall, memory wall, and the instruction level parallelism wall. Okay, I'll explain what is that. So power, as we know, the power is coming from the frequency. Okay, so we, if you know from the electronics point of view, if you're able to finish the clock in a very speedy time, we can able to execute an instruction. So atomic operations, we say. So for any processor or any controller, the very minute opcodes, we say, the time to do perform an opcode depends upon the clock cycle. So that is a very minute instructions we are able to do. So if we increase the frequency of that clock, that means the instructions will be fast, right? So that will make the process or the task fast, right? So that is the power wall. So power wall is basically the technical terms is the frequency CPU. So we can adjust the to do a task. And the problem with this technology is like we want more number of cores to do the this kind of operations. So I have got some. That's why we see Intel i5, i8, 8 cores will be there. So we'll divide the clusters like big cluster, little cluster. Means like for each core we will say, if you're having a graphics function, please try to run in this core. Okay. So all the process of that will be running in that core. So it will increase the number of cores if you wanted to have the fast of way of execution. So for the production, it may make you cost high. Okay. So and the always, if the clock is high, if frequency is high, the heat will be coming. Okay. So that is other disadvantage of this power wall. So when we design, we have to be specific with the clock and the how we are and the number of cores. That's the point on the power wall. And in the memory, we say memory is like basically the RAM we focus on for any system, right? Because when embedded systems get operated, all the instructions will be at the stack which is inside the RAM, and there should not be any scenario. We have seen about caches, virtual memory, physical memory, those terms you would have heard. So there should not be any gap in which the CPU should not wait, or the processor core should not wait for the data coming from the application or somewhere for processing that. So when we design a system, we will ensure that the pipeline of data is flowing into the core, which will makes the system faster. Is again a way of increasing the speed rate. Again, we are getting data at very fast rate, and we are able to process data, and we are able to achieve the things. So all these walls is made to make the things faster. Okay. For in order to tackle this memory wall, we say we invented the terms of L1 cache, L2 cache, L3 cache. So in the pipeline we'll keep. So that is one of the demerit of this memory wall. We have to follow that. Then comes the instruction level parallel wall. That is the then as I told, atomic operations is the way in which we are able to do the instructions at a time. So if I got a parallel instruction set, it will makes the chip fast, right? So if I got a parallel kind of execution, it will make the things should run fast. But the problem is like the speed of the instruction set given to the core should be the same speed. If I am in one core, we are getting more speed, and other core we are giving is in without that same speed, it will execute a different data rate or different process. So we cannot do that. So there is a problem with this this approach where the parallelism is the purpose of how we are going to give the feed the data into that, and how we are able to get this data from there. Okay, so here only single core is needed, but we have to have the bypass of passing the parallelism should happen. So these are the three walls, I think, for any VLSI people, because I'm not that much expertise into the VLSI line, but I have seen one of my papers in my master's. So these three factors only, as when we design a chip, the engineer or the design engineer should focus on. That is the right approach, because if a chip is designed with the high heat, that was the problem with the AMD processor. If you have a laptop from AMD, there was some heating issue. So I'm not telling what the reason for that. But so when we design a chip, we should have these things in the mind. Okay. Then the general purpose CPUs is in efficient for a specific workloads. Okay, so if we have seen our CPU or our laptop or desktop, which is of x86, and we have seen system getting hang and all that. So that's a problem with the with this kind of CPUs or the general purpose CPUs, where they have got n number of tasks. So they are trying to split them. They may miss the data. So which is not needed for a specific application, right? Specific functionality. If I want to design HDMI or this camera sensor, I don't want those actually. So that's other problem which we are not using the general purpose CPUs. Then GPUs have the uh, fixed architecture. GPUs like your graphics card or those kind, they execute in parallelism. For a graphics kind of things, the data should happen in the parallel execution. That's why for the NVIDIA ad we see in the TVs, or if you watch some YouTube and all, you can see the NVIDIA ads in the advertisements. You can see they're having only one core because they follow the instruction level parallel execution. So they will have a fixed architecture which is not needed for the FPGAs. And for FPGA, it's like a it can it must do multiple operations, not a single operations like ASIC, right? So again, that is one of the reasons where we skip the GPUs for this purpose. Okay. So for any queries, any doubts? Hello. Can I proceed further or any queries here?
Yes, sir. You
Yeah.
can proceed.
Yeah, okay, okay. I can proceed or?
Yes, sir. You can proceed.
Yeah. So coming into the emerging demands for the future, AI, artificial intelligence, which algorithms does, it's making the prompt engineering will be the next high thing onto the domain of industry, where many startups may happen, or courses may also happen in the local market, in your towns, how to give a prompt to type a mail to find things. So that's all the AI does. And there comes the machine learning. Okay, machine learning is like trying to learn a pattern. So if you have using WhatsApp, and there is a feature from WhatsApp for the Meta AI giving. So if you wanted to make a birthday wish, it will make a birthday wish, and we can send you that. So if you wanted to add a name in the chat, you can ask, please add this name. So that is the way, and please remove this phrase. Anyone have tried that recently, that application in the WhatsApp? Okay. Yeah, so you can try that actually. So that's the way the machine learning works actually. Then the genomics, which is the DNA study, they're using it. Then comes the cryptography, where the security comes into the picture. The algorithms, when they get how to have an hash or SHA implemented in FPGA, how to use that, and the RTOS, real-time signal processing OS kind. With the DSPs use this kind of data, and how we can able to do that. And the particular design for an FPGA should be need for a configurable, energy efficient, low latency hardware. This point will be clearly matching the first point which I told, the power wall, memory wall, and the instruction level parallelism wall. Okay. Then, as you know, it's a very basic of electronics. I'm just taking part actually. So field programmable gate array field. So that is in which we say compared to ASIC, we can reconfigure the semiconductor device, and it contains the logic blocks, DSPs, memory, and I/O. I have not worked in the development of this. I just used as a driver engineer, just trying to read the data from the FPGA. So how to configure these things I have not tried, but my masters I have seen, which how the VHDL Verilog is implemented using gate log. Is similar way with the functionalities it can be done. So I have checked with my friend who is an architect in the hardware in Intel. So he just told me that Intel also have their own ways of implementing this logic blocks, DSPs, memory. So they will try to do their R&Ds, and they will try to make their own FPGAs and recently Intel took the Altera one to study more about FPGA. I think some people would have heard about Altera company. It was taken by Bosch, taken by Intel in 2015. So in order to have the development into the FPGAs, that's a company which purely was working only on the FPGA. Intel took that. So he was telling me that all the blocks which you are seeing here will be modified according to the architects, their R&D team, their scientists, their research holders, and they'll be making their own architecture, which I have not done. I had just used that for my driver development. Just moving further. Yeah. So this is the definition.
So one thing that are you moving your presentation?
Yes, it's not moving or
No, sir, it's not
okay.
moving.
1 second, I don't know. Now it is moving.
Yes, sir, yes.
Okay. Yeah. Yeah. This way is fine, or I want to go to
Yes, sir,
the.
fine.
Yeah. So yeah, as very basic. As I told, the FPGAs was developed by 1980s by a company known as Xilinx, and today Xilinx is no more. It is again taken by AMD, and they are the one of the leading manufacturers today. But the name has got changed. It's now AMD, and they have gone several number of developments and improvements. Which I told, the performance, power, efficiency is the key in developing any FPGAs. And today we can see a number of spaces where it is being used. Telecommunications, automotive, in automotive it is purely based on the I have worked on the ADAS, so I know how much ADAS chips having an FPGA, and DSPs we have. So we have a separate core for the DSPs and FPGAs for the ADAS autonomous driving, which we are working actually. So I know how much is the importance of FPGA in automotive industry, and also for the high performance computing that we'll discuss in the coming one. So the main reason for using the FPGA is like they have got the parallel processing capabilities with low latency. Latency means the through in which the output is being coming from a chip. Okay, so if I giving an input to a chip and the output is coming within fraction of second, that's having very low latency. So that is the skill of an FPGA designer or FPGA engineer, or the VLSI side engineers or hardware engineers, to have a design to make the design always having the less latency. So if you've seen in your homes, the inverter goes down, and if the current goes down, the inverter will come in some time gap, right? They're able to design a circuit which can still reduce the microseconds of coming when the current goes. That very little time, we are able to get the current back from the inverter. That is the design things actually. So that the FPGA engineers or hardware designers should work. And again the energy efficiency. So if you're having a design where the energy is getting drained, which is not the right approach for the current world, and not because of all these energy resources, we cannot simply use waste. So we should have an energy efficient system. So that's why we use FPGA in high performance computing. Okay. Then there is a graph I'll tell you here. So this is the performance and the power efficiency on your x-axis, and the ease of use, the flexibility of use, how easily you can able to use those one. So if you see, we can see the things that the CPU is very easy to use, right? So it is the height and the x-axis. But if you see the power efficiency and the performance, it is very less. So the CPU stands almost like flexible to the use case for the user point of view, but not with respect to an engineer point of view, like the performance, power, and the other things are not matching. Then comes the GPU, which is almost like a square. It maintains equal on power efficiency and equal on the ease of use. But there's a limitation because it's like GPUs will have a single core, and we have to give one number of parallelism, so which we cannot choose that one. Then comes the FPGA. You can see it's almost similar to GPUs, just below the in use case wise or usage wise, just. And but the performance and the power efficiency is very high, and the reusability is there for the FPGAs, as you know. And for the ASIC, it is having uh, the y-axis is having good power efficiency, but the easy to use is very, very, very difficult. As you have, when we have worked on the ASICs, you had the research people or the working from the VLSI side, they know how difficult to do an ASIC and how much time they may take to design an ASIC, 7 months. So it is again not an easy choice. So again, for a designer point of view, it stands little high here and almost same for the parallelism. So it's a good place to keep FPGA, not place to keep, but the plot makes sure that FPGA is a good guide to go for a low efficiency, high performance, low energy efficient system. Okay, and this is just a comparison between the CPU, GPU, and the FPGA. One is, as I told, is general purpose, which we see for the CPUs, and the GPUs for the parallel processing, and you can say FPGAs for the cost cutting in the long run, and general computing efficiency, high parallelism efficient for the graphics or those kind of things, and highly efficient for a specific task. This is the area where we are always say for a particular task we are able to accomplish. So we don't want that much high parallelism needed, because we want only a single parallelism for doing that. So if you look into HDMI or the camera sensors, we want only to do the camera part of the HDMI, and it is very highly versatile, less flexible, and extremely flexible. So this is I was telling about this point, and again, low the cost of general purpose cost is less, intense cost, and bulk person with which customization can reduce cost for the bulk orders actually. Any queries of I can proceed first? Yeah, then I think no questions so far, so I can we are proceeding further. So as I told, the FPGAs offer unique advantages in high performance computing because of its low latency, high energy efficiency, and high parallelism. But high parallelism, I cannot tell that way, because we want a parallelism where in which not like a GPU kind of like 2 or 3 parallel instructions should run, because we want a specific task to be running. So which makes them easy for a high performance computing systems. So for a high performance computing system, the computing system is means when we are getting a data, how to get that data precise and do it fast. So that is the aim high performance of computing systems. Okay, when you're getting a data from a sensor for a lidar or LED, not LED, lidar or radar. Lidar is like light burst radar for this sensors or the to find out the vehicles nearby, and the higher sensors we are getting a data how to process it very faster to the steering, and we need to control the steering, right? So if you're getting a data with very less time, it may go for a collision for the autonomous driving. So at that time, the computing for this operation should be very fast. It should be within, as I told, when a power supply goes, the inverter comes in a little bit of time. For a automotive kind of place, we cannot have. It should be very minimal latency should be there for doing those kind of driving operation. So we should have a system where we are getting a data with very low latency, which means we're giving an input, the output should come very fast. So that is a place where we say the high performance computing is nearly one of the key features of the which intels in the FPGA's behavior, which we use for this kind of thing. So that is high performance computing, simply computing system which gives you the data in a very fast, precise manner, and we are happy to have that data for our for our other units to take a control on an embedded system or any electronic system or chip design system or chip using chip in which the data are being used. And then coming to the where we say this how it going to work in the sense is like when if you see the architecture for a driver, we have seen if you're trying to open a camera application from your user space, camera space, it is like this kind. But user space in which the users can use the memory, which after a boot up of any or after the power sequence in your mobiles or laptops, up to some point of time you are not able to you're not able to see anything, right? Unless you get the window terminal to type your password, username and password, we are not able to type anything. So at that the point at which up to that is the driver is coming up or driver is booting up. From that only the file system mounted in the file systems only the application comes. So when you're trying to turn on a camera from the application side, should come through a middle layer, and OS is always written with if you see Android OS or Ubuntu OS, it's basically from the Linux kernel. So there will be some IOCTL calls, or that is input outputs control for controlling the driver. So if you wanted to camera should have a video mode, so the buffer size should be more. So when an application guy is clicking a video, the driver guy should have that capability of buffer size more, because he's capturing the video, and video is a group of pixels, not pixels, it's a group of images put in a frame, which looks like, feels like it's like a video. So many capturing will happen within a fraction of seconds. 30 psi something they will tell for that kind of operation. So that's so at that time. So we have this thing. So that's again what I was coming to tell is that, so when we design a system, so this kind of thing should be faster. So that's the reason why the FPGAs have to be one of the applications of FPGAs, like this throughput will come very high. And so if you get the data and we are able to put the data in a very fast manner, it is very good. So suppose you have an HDMI connection, or or the camera part I told it for HDMI. So if we connected HDMI to your home television or somewhere, and the data is not going that much fast, means you may feel the lag, which is not good, right, for a design point of view. That's why these FPGAs come into picture, or any low latency device come into picture, where the data is seen or processed very fast. That is, in a way, it's none of the high computing. If you are able to do some computing operations with the data we are getting for an HDMI, basically we'll have the two types. The screen size will change, so 1920 into 960, some ratios will be there, or other mode will be there. So there will be like two set of matrices will be there. But other cases like in autonomous driving or ADAS, autonomous driving and ADAS is very different. Okay, so if you are from this, I'll tell, like ADAS is like driver assistance actually. So when you're taking a car to the backside or to the sideways, it will give you a suggestion like what is happening in the sideways, driver assistance. That is driver assistance. And autonomous driving is without the driver. We are able to control the car and take it to a place from the Google Drive, from the Google Maps will be collecting the data, then it will just keep on moving on with that. Car will be going on, and the sensors which is attached to the car will give us the data on the road. And according to the steering will be controlled, according to the brake pedals, accelerator, all will be controlled. So that is the difference between, I was telling, of ADAS and autonomous driving. And again, as I told, for this, when we are trying to compute the data, low latency, so FPGA or any other like ASICs, those kind of things comes to that actually. And our topic today was FPGA. I was just focusing only on FPGA. There are other technologies which other sources like ASIC also can be used for this feature, but the reusability, efficiency, there are reasons which may we have to focus on FPGAs. Then what are the advantages of having FPGAs in high performance computing? One is the parallelism. They have very highly parallel and can do the multiple computations simultaneously, and which in sense, but when the parallelism comes, all the data should be in a single core. So that's why we can tell for multiple occasions we can use that. So if you want an HDMI or configurations, or for a camera sensor, we can use for either for photos or videos. Slight modifications can be changed in the parallelism in the from an FPGA point of view, because when we do the parallelism, all the instructions should happen in a single core. So in a single core we cannot load, but so if you cannot load means you can handle some operation, not like ASIC. ASIC is specifically designed only for that purpose. But FPGA, if you're like look for a camera sensor, we can use for recording if video, or we can use it for capturing some images. So that is the one of the reasons of parallelism. But the problem is parallelism, as I told in the three walls, it is having the single core of doing it actually. And there is specific algorithms compared to GPU, CPUs for doing that, and having a low latency, which I told, which is a critical for many PC, which is high performance computing. They can perform the computation with minimal delay. As I told, the use case of inverter or the autonomous driving for the financial, that also in the financial trading, network packaging, processing, and email processing. Email processing example is you can take as this autonomous driving, and for this network packet drivers, of if you are going for the like switching from Wi-Fi to this kind of data network, how much fast the data is reaching to your, if you are streaming a YouTube in your phone. I was on a data, mobile data, and I suddenly turned off my mobile data and I'm turning on the Wi-Fi. So the communication protocol for receiving the data is different. One is from the Wi-Fi, one is from the, so OSI model. If you take the physical layer, there's slight difference, but still, for a computing point of view, we should not wait for the YouTube should not get stuck. So minimal delay in changing the Wi-Fi to data, mobile data, should happen for a network driver. So that is the thing they were telling on this point actually. Then comes the energy efficiency. So energy efficiency is the way in which the CPUs compared to GPUs and these things, how efficiently we can use the energy. So for any embedded systems, if the energy is high, the power will be going high. So if the power goes high, heat will come, and it is simply draining the resources. Again, we need to charge it. So again, we are trying to use the electricity, which is not good, right? So we have to design a system always which having less energy using capability. So FPGAs do that, and it has the flexibility of changing from one place to the other one, which means it can do a set of functions and making it highly easily adaptable to this kind of applications. And FPGAs are easily customizable in the forms like, as I told, for a camera or this camera sensors, we can either go for recording. Again, we can change the camera resolutions, the frame, bits for frame, those things. So it's easily to customize actually, and it's also having the high bandwidth for doing the real-time data, is because it's parallel processing capability. So that is other one of the advantages of having using FPGA in the high performance computing. So in the future, one of the slides we're telling about the future of the FPGAs, how which all fields it can be used. One was with the artificial intelligence and the machine learning. So they can give if many of the you had about the neural networks, then the PY flow sensor architecture, those kinds of machine learning algorithms, sensor flows, all can use this kind of, because again this for all this artificial intelligence is again the parallelism should happen. So it is a way in which we can use that. Then the big data analysis or analytics, we can use this. It can, because of this less latency, we can able to use it for the big data. Then the network security. Now security is a key feature in the coming world. So if the autonomous driving and ADAS is coming to the Indian markets, it will happen in Indian markets within 3-4 years. It will be it's going to come into the Indian markets as well, and it can able to run its own. So there are many queries like in Indian roads that the autonomous driving or ADAS will be working or not. Definitely, it is going to come for any, and it will be coming in very in the common cars also, not for the premium cars. So when the technology is being developed, it's of the industry to have those technologies to made easy to the common man. So in India also will be having this kind of technologies coming ADAS and autonomous driving. At that time when this feature comes, someone should not hack our car like a mobile hack should happen, or I've seen so many cases like that. Any queries so far? Yeah. So yeah. Then comes the net security. So our cars should be not cannot be. We have seen many movies in which if you're having a heart pacemaker and they're trying to hack the pacemaker and the patient goes dying. So in the future things may happen like the car with ADAS and autonomous driving can hack, and they can collapse the car somewhere, and they can do some illegal like some human threats to the people. So network security, I in the ADAS domain I had a chance to work for some time with security. So we have seen how we can secure a embedded system with security protocols. So hacking is a method in which they are trying to hack the system. So as a security engineer or network security engineers, they will have some ways to stop that. So as you know, the security there is based on the cryptographies, algorithms, SHA, or DSA, then those kind of algorithms. If you implement those kind of algorithms using FPGAs, having little kind of parallelism, it's very easy to the user will not get the time to encrypt the data. So it will happen very fast, so that the hacker have to be little bit faster enough to process this data, and he can hack the system. So at that time, this network security will plays a key role for the FPGAs in the future. Then the cloud computing now. Cloud computing, as you know, there are like if you are working in the industry, we say we have it builds today morning. So the developers which are working today, they will merge the code today and they have to push to the main branch. You say. And the day after tomorrow, they will have the customers we need to give the binaries to some customers every day. Okay, so that their testing engineers can test it day by day. So these things will happen autonomously. So when we merge a code, it will go to the server. It will try to in the night. There's a time for that. Up to 9 o'clock only the merging will happen. After the 9, the system will go for autonomous build. So it will build the code. It will generate the binaries. It will send to the customer, and on the next day morning, the customer can flash it and see the features which they told they committed on this day is working or not. So that is the cloud computing. There are so many tools like Accelerators, so many tools from Microsoft, so it also uses this. So at that time, again, the network, so many areas they can use the FPGAs in this development. And the scientific stimulations, as I told, there's a genomics where with the GNA case study where they can able to use the FPGAs for their operations actually. Then the FPGA architecture. So it's a normal system on chip architecture where we can see the blue color, the speed core eFPGA IP, intellectual property. So every chip we make with intellectual property. It's there are ways in the industries to protect the data. One is like IPs, intellectual properties, then copyrights, and then the patents. So in the industry, you generally use the intellectual property concept for the chip. So you can see the caches, all the things which we discussed in the first slide. If you remember the 3 walls, you can see DDR is for the memory wall. Then comes the cache again for the memory. Then the processor cluster. Then Ethernet. That is all about the PCI Express is one of the buses in which the data transfer is being happen. So as I told, it refers to the structural design used to offload and accelerate the computing interactive task onto an FPGA actually. So this is the area where a lot of hardware companies like Intel or the AMD previously Xilinx all works, and this is the part which I do work on when I having when having kernel, because I'm from the kernel side, so when we have an FPGA, so there is a way in which how to get data from a driver, and we have to accelerate the data which we are getting. So we need to write a buffer here. We need to collect the buffer very fast, and we say write or ISCTL, not ISCTL, we'll say PCI, write PCI, read, those kind of things we will discuss here. And second memory part where which we have to use for the memory kind of the data. Yeah. So this is the basic architecture. There are so many companies working on this, on modifying how fast, with low fat latency, high speed, power efficiency to get the data. And if you know from the electronic side, there are some problems with capacitors, transistors, and what is the latency, how it goes slow. We have to find a way, so we have to find a solutions in which we can do that. So I do always believe the basics is the way in which the circuits are being brought. So if you are able to design the very basics of the transistors or the diodes or those kind, then only this latency or this efficiency comes into that kind of which the FPGA engine of the hardware engineers is working on. Moving further. Yeah, so I told this, there are so many cases in which we are able to use the FPGAs. One such area is the Microsoft Brainwave project. You can also search this in the Google as well. So this is a survey done by the Microsoft on the brainwaves. How we can able to do that using AI, how we are able to get the data on the deep learning. So real time artificial intelligence, how we are going to use and low latency, how we are able to do that. The ping search, how much fast we are getting. Ping search is like when we are giving something data like your place name, something, how much fast it is coming and which site is coming up. So those kind of data. So they are trying to think with the brain how we can easily pop up your data. So if you're searching a hotel nearby or anything, so how my hotel should come in the first. So that is the big search ranking. Also, those kind they can use. So you can just learn how this Microsoft Brainwave project works on FPGAs. And you can, I say, from a business point of view, there's a lot of scope here. Students also, there are like a number of ways you can see for the researchers. Also, you can see how we can easily do this actually. Yeah. Then, as I told, the development tools and the ecosystem. So for anything you have seen about close computing, you have seen close computing and non-host computing. Non-host means like you are writing a C code for a Windows system. That C code generated output we can run in all Windows systems. That is the non-cross compile. So if you're having a Android phone, if you want to modify some data or some drivers in Android, we have to do some modifications in the Android code, which is not x86, which is an ARM processor. So that's the tools and the ecosystem. So they plays a key role in having the design flow. So if you don't have proper tools, it may affect your development activities. So if I remember in my masters, I have done my final project on area efficient ladder Fisher. So I have got silings and models in to show the difference in two systems. I still remember actually the timings was shown in that graph and how it varies from system point of view, from the tools point of view, how efficient, how that changes. So tools plays an important role because from a research point of view, it plays a very hard role, very important role because before going to the development, we should know the throughput or we should see the latency. So it plays a very role in development this tools and ecosystems part. And if you see the ways in which we can implement this kind is like, as I told, there are like in the leading industry, there are like two guys leading the market. Previously it was the Xilinx and it was Altera. So you have seen in the those who have done your engineering from maybe some 10 years back or 2 years back, that I've seen this Altera heard in the textbooks when I also heard that. Now there is no more Altera and no more Xilinx, though Xilinx was taken by AMD. And Altera is part of Intel now. So they changed the name of the Altera board to the Cyclone statics, something those kind. That's my friend saying from Intel. So those are the tools which they have used, and how to give this RTL to the bit stream way. So when you have a bit file, how to get the implementation done. So the Intel have their own ways of doing, and they will have their own ways of doing. So the tool changes. So if we have if you have photo, how to edit the photo in a Photoshop as well as another Microsoft photo editor. So it varies how the framework of Lightroom, how so the tools plays a very important role. And if you come to the Xilinx part, it can be written in C. Now there is a technology in which when I used to write code, writing the VHDL very long codes, we will follow the uh, structural programming for the VHDL are very long. We have to write the gate level. From there we need to start. So now there is a way in which you can write in CCPP and convert to this. I have not tried that, but I just saw the pages or the application which does that. So it makes us very easy to do the because Verilog and VHDL programming was really tough at those times. If I remember, I don't know the current scenario, but when I used to write this, it was tough. But there are ways in which, with the help of HS, this AI comes. This was easily done. So the Xilinx can be written in C and CPP, but the Intel they are telling you please write only in CPP, and it is mainly for the high speed one. This is only for the DSP. So the Xilinx ones is for the high speed designs, and the Intel ones are basically for the DSP heavy applications actually. Okay, then open computing language. So there was a way in which so there are some in models. If you take it, you can write a code in VHDL and Verilog. So it's OpenCL is open computing language, which was able to do all this in a single time at those times. But I don't know the current scenario of that. And coming to the source frameworks actually, which is FINN, and for the neural network based, other is the Chisel and Spinal. Still I have not worked, but I just asked my friends and they were telling Chisel is basically for the risk reduced instruction set, which is basically for the ARM based, and it is basically for the academics and the people can use Chisel. And Spinal HTL is basically for the ASIC and FPGA implementation, and there they support Verilog and VHDL. And other comes to Fin, which is only for the neural networks and the binary format, and it will support all the binary format for these neural networks. And challenges actually, it is having a lot of challenges. As I told, one is the if you work in the FPGAs and ASICs, it's a we need an expertise actually for designing these things, and it's having a long development cycle, and it is not easy to have that silver bullet kind of thing, so that we have to have some struggles in getting it, and the cost for the mass production and for the less number of production, and the tools change as I told, the OpenCL those kinds of it less, so we have to focus more onto the tool part in that things. And this is the future. Maybe the researchers, faculty, students can work on, or where they have interest, they can look into these topics. But the FPGA in the cloud, as I told, this FPGAs were part. I was telling how a build system is built on that. Able to do that, and this is again one of kind of these things. And the chiplets, FPGA integration, autonomous design tools, how you can use the AI, FPGA place and do the things, and the open source hardware risk, which I told, which these are kind of things which are working, and soft process, how they can implement that. So near memory computing, FPGA with this high bandwidth memory, how we can use those kind of things. So this is areas in which you can work. So for a research point of view, from an industrial point of view, if you are able to make a tool, that's a good part. If you are able to make a framework, that's a good part. For a company point of view with IPs, integrate for the intellectual property from a research point of view, because I have not gone for any research, so I have not. And that's all. What I heard is like they'll be more focusing on the design part, which if they're trying to change this part, what we're going to have the design, so that they will compare the graphs of the thesis which I done in masters, or it is continuation they were telling for the doctoral degrees. So they will be having case studies how this guy is working, how that guy is working. That is how the researchers work actually. So, and according to the grades, they may have their own solution, their own ways, but the industry will not work that way. And we will be more focusing on the tools change and anything we develop is a patent or it's an intellectual property for the industry. So, so an engineer or electronics enthusiast should have a bridge between the industry to the research. So that is the bridge which the companies are also looking. All the in electronics enthusiasts also should look. This bridge should narrow down with the broader broader base, so that people can able to work. The researchers can able to work to the industry straight away, and the industries can able to straight away think on the architecture point to the research side. So spending equal quality time with industry and research should happen, which should happen. That's the right way. Otherwise, it's like an again academies. Academy happen with the industry, and the industries if we stay far away from the research, which should not be the ideal scenario. These 5 year programs, I don't know why that's happening, but still, those kind of things they can have to think on that actually. Now, the educational research opportunities for the faculty, students, there are courses which they have for the VLSI design, reconfigurable computing, and high performance computing. Also, there are researches happening on the energy efficient AI, classical interfaces, real time systems, and the grants, NFA for and industrial partnerships with Xilinx and Intel academic programs are there. If you have that, you can join the academy, they will give you their things, you can work on that, you can design your things. So, when you're having that much passionate for research, they can come to the industry, they can do those. Similar way from industry, they can come to the academy and see into the research side what we can do with the design point of view from an architect point of view, and how to design a chip with low latency. That should be the aim, and it should serve the people and the country. Yeah, so we are concluding off, and why? What is the what we done for this 1 hour was like they have unique blend for flexibility, efficiency, and performance. And it is not a replacement actually. It's GP for GPUs and CPUs. It is just an accelerator, just for a particular thing which can be reused. So in the cutting edge computing and specified high performance computing, it can be used. Edge computing means the OSISO layer, the last layer, physical layer, where the data is moving from the Wi-Fi out or from the Bluetooth out. So that is the edge computing. And we want to have a multidisciplinary skill. So there's a saying from a computer engineer, like one who knows coding cannot be a program engineer, one cannot know soldering, cannot be an electronics engineer. Should have the both combi, then he becomes an embedded engineer. So the both skills should be there for a embedded guy. And from a design point of view, that's a different story. I can tell from the OS point of view. Yeah, that's from my end. And if you have any queries, you can mail to me. And this is what which I have taken for this PPTs, and signing off. Any questions you can ask.
So, anyone have any questions? If you have any doubt or queries, please ask. Okay, sir, I think no more questions.
Yeah.
So, thank you, sir, for taking the time to share your knowledge and expertise. The session was highly informative, and it has been highly beneficial for all participants. And we really appreciate your effort in making it so impactful. Thank you so much, Ayyappadas sir, for the session.
Yeah, thanks, and thanks, Nana King sir, for me the opportunity and the platform which was given to me actually. So thanks for that. And if you have any queries, you can just mail to me. I can help of my knowledge onto this. And signing off for this time. We meet. So thank you all. Thanks for your time.
So participants, the feedback link is in the chat box. Please fill it out. So thank you so much, and let's see you tomorrow again. Thank you.